Hello, welcome to this presentation of the International Conference on Soft Computing Models in Industrial and Environmental Applications, SOCO, to be held in Burgos, Spain in September 2020. The title of this talk is Functional Networks for Image Segmentation of Cutaneous Lesions with Rational Curves. My name is Andres Iglesias. I belong to the Department of Information Science, the Faculty of Sciences at Toho University, Japan, and also at the Department of Applied Mathematics and Computational Sciences of the University of Cantabria in Santander, Spain. This work has been done in collaboration with my colleagues Akemi Galvez from the same institutions and Professors Itzhak Pfister and Itzhak Pfister Jr. from the Faculty of Electrical Engineering and Computer Science of the University of Maribor, Slovenia. Well, this is the outline of my talk. First of all, I will talk about the motivation of this work, then about the method used to solve the problem. Then I will explain a little bit about the functional networks. Then I will proceed with the experiments and results, then the conclusions, and finally questions and answers. So basically the motivation is about the skin cancer, in particular melanoma, which is one of the most frequent and most dangerous types of skin cancer. If you take a look at the figures I have here in this slide, we talk about more than 3 million cases and more than 60,000 deaths in 2015 worldwide. This is a very important clinical problem, a medical problem, and for that, early detection is critical for survival. You take a look at the survival rate for different stages, starting in stage 1, which is between 95–97%, but it is as low as 7 to 20% of survival for stage 4. So early detection is very important in order to survive from this disease. But one of the problems is that melanoma is very difficult to distinguish visually from other skin diseases, such as carcinoma and other problems. So basically, the methods we have to identify melanoma, such as the ABCD method, the 7-point checklist, the Messier scale, on different kinds of biopsy, rely strongly on human intervention, and the one additional problem is the different diagnostic results change from dermatologist to dermatologist. So they strongly rely on experienced dermatologists, but even in this case, they can vary from people to people. The first step in this diagnosis is to classify the skin lesion as being benign or malignant. And this involves image segmentation, which requires border detection, which is basically to determine what is the border of the skin lesion taken from dermoscopic images and other kind of images. So you have to distinguish which is the real lesion from the image background. And basically the procedure is based on the visual interpretation of images, and therefore is prone to errors. So it is important to determine a semi-automatic diagnosis method for this based on computer. In order to do this, our approach is to consider a free-form rational Bézier curve given by these equations, and then given a set of feature points which are assumed to be obtained by a trained dermatologist from the collection of points from separating the lesion from the skin background. The goal is to obtain the rational curve minimizing the least square functional error given by this equation, which basically means to perform data fitting in order to identify this border curve. Okay, so this means basically doing some maths written here. The details can be found in the paper. Basically, to solve call it the normal equation. This is a very hard optimization problem because it is continuous, it's overdetermined, it's nonlinear, and it's multivariate. So the approach followed here in this work is to apply functional networks. In order to understand functional networks, I have this example. You can find more details in my book, Functional Equations in Applied Sciences. But basically, the idea is that we have a network which is a powerful extension of the neural networks. So functional networks can be understood as an extension, and as a powerful extension of neural networks, in which we have several arguments. The neural functions in functional networks have several arguments, also can be multivariate. The neural functions can be different, while in neural networks they are identical, and also there are no ways but functions instead. So basically what happens is that the neural outputs can be coincident, leading to a set of functional equations which have to be solved. In particular, in this work, we consider this functional network. In order to solve the problem, we have to learn the function phi of tau, which in turn requires to learn the different component functions and the poles in the expression of the functional error. And this requires a learning process for the polynomial functions and the ways involved in this expression of the rational form. Here we have some illustrative examples. Basically, we start with a benchmark of 12 different medical images taken from a public repository. I display here some examples just to illustrate how difficult it is to identify which is a benign or malignant melanoma. Here you have different examples. As you can see, they can vary a lot in size, in shape, in color, in volume, and other properties, visual and medical properties. So it's quite tough to distinguish which ones are melanomas from other skin lesions, and actually with even among the melanomas which are benign or which are malignant. And here the results we get. In this table we display the results for the different examples are shown in the first column. We have 12 different examples in our benchmark. And then we have different methods: thresholding, clustering, the polynomial feeding, a multi-layer perceptron neural network, and in the last column, our method. And best results for each example are highlighted in bold. So as you can see, basically with our method, we get fitting errors of the order 10 to minus 2, 10 to minus 3, and in most instances of this benchmark, our method outperforms other methods available in the literature. So, as the conclusions, in this paper we address the problem of image segmentation for medical images of cutaneous lesions, in particular melanoma. We seek to compute the border curve separating the lesion from the image background. The curve is constructed through data fitting from a collection of points lying on the lesion boundary. In this work, the boundary curve is assumed to be rational instead of polynomial, which is the most common but also simpler case in the literature. In order to perform this data fitting, we address the problem by using functional networks, which is a powerful extension of the classical artificial neural networks. And the main conclusions of this work are that the method performs pretty well. It actually outperforms the polynomial approach and other classical approaches in the literature, such as clustering or thresholding, and also multi-layer perceptron neural networks, in terms of accuracy for all instances in the paper, of almost all instances in the paper. But this method is probably not optimal yet, in the sense that it can be further improved. And the main limitations of this work, as we have to determine the degree of the curve, even if it is rational, we have to determine which is the degree for the numerator and the denominator of this rational expression. And then some parameters have to be properly tuned. I mean, for instance, the number of neurons related to the size of the data. And also, we still rely on human intervention to determine the feature points. I mean, the points used to perform the data fitting. So there are some limitations we have to deal with in the feature work. So this is the end of my short talk. Thank you very much for your attention. We'd like to first, finally, we would like to thank these sponsors: the Spanish Ministry of Science, Innovation and University, the SOCO72, the Regional Society of Cantabria, the Slovenian Research Agency, and the European Commission through the European project PDA, involving several partners shown here. Thank you very much for your attention.